if you take 14 steps, the stride length would be small. So he was asked to optimize, and after doing that optimize, he came to either 12 steps or 13 steps. So the total distance by which he will be covering with steps just by simple running, not hurdle jumping, has to be a multiple of 12 as well as 13. So it has to be a multiple of the LCM of 12 and 13, isn't it? We have done this problem. It has to be a multiple of 12, it has to be a multiple of 13. So it has to be a multiple of 12 as well as 13. And 13 being a prime number, the LCM is just the product, it is 156. And the nearest number to 35, which is divisible by 156, is 31.2. So that's why 3.8 was sacrosanct. And if he had taken 12 strides, the stride length would be 2.6 meters. If he had taken 13 strides, it would have been 2.4 meters, well within his maximum possible stride length of 3 meters. And he later on settled for 13 strides, odd number of strides. Because if you take even number of strides, while jumping the hurdle, you are giving pressure on one particular leg. And it is repeating. But the physical efficiency, I think, becomes more when it alternates between left and right. And so if you take odd number of strides between two hurdles, then consecutive hurdles you are crossing by giving pressure on left, right alternately. It alternates between the two legs, and that's how he clinched. He had practiced for 13 strides between two hurdles. So that's how he had organized his run. I also had this Valerie Brunel, something what Dr. Chakraborty was showing. You can see what he said, that the height of the CG and the height of the bar are same. And then he had done that elaboration which was very flawed. I'm not going to elaborate. And these are the villain about which I was talking with the director, where mathematics is used with a great extent. You can identify them? The students can't identify them? Duckworth and Lewis. I'm not going into the elaboration, but you know how much mathematics is used in deciding the fate of the required run rate for the team which is batting second, and that is due to Duckworth and Lewis. And I agree with our Honorable Director that it needs modification. Now, can you identify this person? Nadia Comaneci in 1976 Montreal Olympics, and she scored a perfect 10 in gymnastics. Now, the numbering in gymnastics also has a lot of mathematics in it. A gymnast has to perform 12 exercises, and each exercise is evaluated by 7 judges. Out of the 7 judges, the highest score is taken off, the lowest score is taken off, and the average of the remaining 5 are taken, and this is done all across the 12 compulsory exercises. And then there will be some optional exercises, but for each optional exercise there is a degree of difficulty. So if the degree of difficulty is 1.2 and you score 8, then you actually score 8 into 1.2, 9.6. And like that, the total marks is obtained and it is averaged out of the total number of scores. And Nadia Comaneci was the first one, as a 14-year-old girl, to score perfect 10 in this gymnastics. And I'll just conclude by again giving you an excitement about the Queen. And about this Queen, in fact, you know, in mathematics you come across thousands of equations, but Robert Feynman, in the year, if I recall correctly, 1977, had considered this equation as the jewel. This equation is the jewel, most fascinating equation in mathematics. Why it is the jewel? Well, many students may be in class 9 or 10, but at the later stage, you will know that E and pi are transcendental numbers, and I is the fundamental imaginary number. So, e to the power of I pi is quite a complicated expression, but that is equal to -1, and this was established first in 1748 by none other than Leonhard Euler. And you know, for best part of his career, Leonhard Euler was visually impaired. So again, this is my dream, that you think mathematics, and definitely at that time there was no software for the visually impaired person. So he was thinking mathematics, and this is my dream, that all the students and I'm not using words when I'm saying that it is my dream, that they should think mathematics and treat it more as a queen than as a servant. A dream, in the words of APJ Abdul Kalam, that you dream with your eyes open. The dream that comes during your sleep is something on which you do not have control. You dream with your eyes open. Think mathematics. And when it comes to dream, I cannot resist my temptation to quote these lines from William Butler Yeats. Last year was his 150th anniversary, and many of you will be knowing that he was instrumental in introducing Tagore to the Western world. Tagore got the Nobel Prize, the first in Asia, in 1913, whereas Yeats got it in 1926. And he has contributed significantly towards our country getting that glory, of course, through Gurudev Rabindranath Tagore. So he had written this about the dreams. Had I the heavens embroidered cloths enwrought with golden and silver light, the blue and the dim and the dark light, of night and light and the half light, I'll spread the dreams under your feet. I being poor, I'll spread the dreams under your feet. Had I got those cloths, I'd have spread that, but I do not have that. I only have my dreams. I'll spread that under your feet. Tread softly. Aste padokkep rakhun. Tread softly, because you are treading on my dreams. Thank you very much for giving me the opportunity.
I'm sure you will all agree that with what Dr. Ghosh started saying, that it may be a dry subject. I don't have to say anything, whether it was a dry talk or one of the most illuminating lectures. It is for you to decide. Mathematics can be fun. Mathematics is the queen of science. That is something which, especially the youngsters here in the audience, they have to appreciate in their would-be career, which is going to span so many decades in the future. The only thing which I would like to say is that maybe theory of numbers, which I mentioned in my address, that is, the theory of numbers is today becoming extremely useful in there are various subjects. One subject is cryptography, and cryptography is a subject which is used tremendously, and many of you will be knowing it in details at the subsequent days, where the theory of numbers is being used. And we don't have to look at others. We have our own Srinivas Ramanujam, who is a doyen, and I think he's an absolute essential singularity which cannot be removed. So with that, let's express our wholehearted thanks to Dr. Ghosh once again. Okay, so we are running a little bit late, but it doesn't matter. We will manage. Now, so the next talk, in fact, the last talk of this two-day event will be by our colleague from Theoretical Physics Department of ISCS, Professor Soumitra Sengupta.
So I thank the organizer of this event for asking me to speak here, because it is always nice to be speaking my own place in front of my own colleagues, and of course many bright young faces from various schools. And all of you know that the discovery of gravitational wave has created a sensation all over the world. And in this talk I will just try to explain that why we consider this discovery is probably the discovery of this, suddenly of this century, and maybe one of the most significant discovery in the last 100 years. One thing that I was told that considering the heterogeneity of the audience, I should not use any mathematical equation, but the subject is essentially mathematical. So I have tried my level best not to use any mathematics, maybe barring one or two very small equations, and I'll try to explain the basic concept without getting into the details of the technicalities of the subject, that what it is all about and why we are so excited. So it is, my effort will be to share my excitement with all of you. So, before I start, I would like to tell you that actually when we stand, when we do science sitting on this earth, try to imagine that, consider our planet Earth, and you know its diameter is approximately 12,000 kilometers. Then you see the Sun, which is our closest star, whose diameter is given by this magnitude. You can see the number. And then you can see the solar family, the Sun and with the planets. We stand here and you can see the size. It is gradually increasing, 9 zeros after 1. This is the size of the solar family, and Sun is the star. And then our galaxy with size 10 to the power 18 kilometer has 10 to the power 11 such stars. And finally, what we have seen so far, there are 10 to the power 11 such galaxies, and each galaxy, the average distance between them is approximately 10 to the power 20 kilometers. So now you understand the universe where we are sitting. And then, of course, somewhere here, maybe here, Earth, we are here in Calcutta in ICS, trying to say something. So it's indeed a very, very ambitious thing to do. And we will try to explain that in the last 300, 400 years of modern science, what we have achieved. So, with this background, the thing that we are handling, first let me tell you that the most important thing of nature is force. Because all of you know that Newton taught us, and we know from our childhood, that if there is no force, nothing will happen. A body rest will forever be in rest. A body in motion will forever be in uniform motion, and it's not interesting at all. So everything that is happening around you, every interesting phenomena is because of some force. And so force is the cause of all changes or dynamism in nature. And remember, the two main forces are electromagnetic force and gravitational force. And I can show you that almost everything that is happening around you are largely because of these two forces. And you know about these forces. Electric magnetic force and the gravitational force. So all the phenomena in nature are because of these two forces. I mean, there are other forces, but those are not that important in our daily life, observable world. So, with this understanding, first let me tell you that we know that electric charges have electric fields that you know, and they can apply electric forces on another charge. And then you know that if that charge starts moving with velocity v, it generates magnetic field around it, and which can exert magnetic force on another moving charge, or what is we call in common language current. So current is a moving charge, and so it produces magnetic field, and we know that this is what is called electric magnetic theory, because it is Maxwell and Faraday, they showed that they are intimately related. And so electric and magnetic forces are the forces responsible for everything, that whatever you see, all the forces that you see are electric and magnetic forces, except the another force which is called gravitation, about which we will discuss. But remember, these charges which I showed, when moving with velocity produces magnetic field, if it starts accelerating, suppose moving with non-uniform velocity is changing, then what happens, it was shown by Maxwell that this electric and magnetic field starts moving, starts traveling. So they become a non-static moving field, and which is commonly known as electromagnetic wave. So it is caused by accelerating charge. And they have certain characteristic that the electric and magnetic fields, they vibrate in two planes, in a plane where this, and the direction of motion of that electric and magnetic field as a whole, they move in this direction with some characteristic wavelength and frequency. And we know that this light, X-ray and whatever you see around you are basically electromagnetic waves. So, for example, light, X-ray, etc. are electromagnetic waves. They travel in space-time in vacuum with speed given by this amount. It's a very high speed, and we know that they travel at a very, very high speed. And this can travel with much attenuation. It can travel very long distance with a very high speed, and therefore this is the mode of communication in modern civilization. Whatever you are doing in your mobile or in your television or whatever in modern day, any communication that you are doing are essentially electromagnetic wave transmission. And interestingly, this transmission was first shown in this city by none other than Professor J.C. Bose by sending a signal from Calcutta University Institute Hall to Presidency College. This was first received, and it was this wireless communication through electromagnetic wave was discovered in this city, and is our mode of communication in modern civilization. So, this is the wireless communication. We know that this accelerating charge emits waves. This is a transmitter, this is a receiver, and this is essentially whatever is happening even in your mobile set or in television or anywhere. So this is our mode of communication. Now, naturally, the question that arises, it came from that fundamental force, electromagnetic force, which gave rise to this field or this wave. Question is, what happens for gravitational force? Does gravitational field can travel like a wave with a finite speed? This is a very natural question. This is the only other important force. To understand this question, first let me tell you what was our understanding before Einstein. We all know that Newton explained the force of gravitation by an apple falling from a tree, and he also explained that this is being attracted by Earth by a gravitational force, but the same force is responsible for the motion of the planets around the Sun. This is remarkable that this gravitational force is universal in character. And he said that this force between two masses is given by a constant called Newton's constant times the product of the masses divided by square of the distance. Now remember, every force is characterized by two quantities. One quantity is how far it is extended, the range. And you can clearly see this force is extended up to infinity, because only at infinity the force goes to zero, otherwise it is extended up to long distance. But another important thing in description of force is how strong is the force. And this is given by this constant coupling, which for electric force is the charge of an electron. But for gravitational force is the Newton's constant, and this has a very, very small value. And therefore, unless these masses are very, very large, this force is so insignificant that you cannot see it in your daily life. And for this reason, this object and this object are keeping on the table, they are attracting, but they are not going towards each other, because this force is so small. Because their masses are small, therefore they cannot overcome the frictional force on the table. And frictional force incidentally is the electromagnetic force. And therefore, this Newton constant being very small, unless the masses are very, very large, the forces cannot be significant. And for this reason, the gravitation played an important role only for large mass objects like Earth or planets or star or big things. So it is going down because though its mass is small, but mass of the Earth is very large. Now, with this law, Newton very successfully explained planetary motion. Okay, I think I should point point out one more thing, that this force can also be large when mass is small, but also it can also be large when the distance between them is very, very small. So if two objects can come very, very close, which is happening in the Large Hadron Collider when two proton beams are coming very, very close, this might give rise to a large gravitation. So, but that is a different story which I'm not addressing here, but I'm just pointing out it. Okay. So, the thing is that for large objects this force is significant, and Newton applied this to explain planetary motion, and he did this very successfully. But according to Newton, the gravitational fields act instantaneously. By this he meant that suppose there is a mass here, and then you bring another mass here, the moment you bring it instantly the force is created. You can see that there is no time factor here, it is created instantly. So, the moment you bring the mass, it instantly experiences the force. So, the gravitational interaction is transmitted instantaneously with infinite speed. So, Newton said that unlike electromagnetic wave, the gravitational field acts instantaneously and does not travel like a wave with a finite speed. So, it is just an instantaneous action. So, we understood that probably the gravitational wave is not possible. But then came Einstein with a revolutionary idea. He said, Einstein gave a new understanding of gravitational force which is not at all similar to what Newton said. And once again, this is a revolution, because sometimes a discovery is something where something exists, you modify it. But sometimes a discovery is something where you completely uproot it and bring a new idea. So in this sense, Einstein's understanding is a revolution. So what he did is the following. He said, Einstein rejected this concept of force between two masses. So he came out with a brilliant idea. Idea was the following. He said, consider a surface where from your childhood you have learned the geometry that sum of the three angles of a triangle is 180 degree. The shortest distance is a straight line. Circumference of a circle is 2 pi r. You know about this from your childhood. But the thing is, this is what is called Euclidean geometry, no longer holds in this case. See, suppose consider the surface of a ball, surface of a football. Draw a triangle. The sum of the three angles are greater than 180. This is flat, so this is equal to 180. But if it is, instead of being convex, if it is concave, then the sum is less than 180. So our usual understanding of theorem of geometry starts breaking down. But what Einstein did is the following. Einstein said that Newton's idea is that body travels along a straight line, either 6 or odd straight line, if there is no force, and it accelerates. So something accelerating in a curved line, so it's the direction of velocity changing, something accelerates when there is force. That is exactly what first law of Newton that you are learning from your high school. Einstein said, no, this is not happening. What is happening is the following. So Newton's idea, no force, straight line, in presence of force, suppose this is, as Newton thought, attracting, so it is because of attraction, it is moving in a curved line, means acceleration. Einstein said, no, there is nothing called force, nobody is attracting anybody. What is happening, that object, this mass m, is changing the space around it like a curved membrane. So suppose I have, let me show you. Suppose I have this sheet of paper and this is like this. See, the shortest distance between 2 points is a straight line and you travel along a straight line in absence of force. But suppose, because of the mass m, this gets curved. Now you have to be on the surface. So the shortest distance is not a straight line but a curved line. There is no straight line. There is no straight line on the surface and it is travelling along a curved line, and looking at that it's a curved line, you are saying that it is accelerating and therefore there is a force. So So Einstein said, this is a remarkable understanding. He said that the space gave